Hello students, welcome to online video tutorials. Myself Dr. Chayabhyam, Associate Professor, Department of ECE. In this video, let's look into the concepts of wavelength division multiplexing, WDM concepts and components. In this module, we will be understanding the concepts of operational principles of WDM, WDM standards, MZI, multiplexers, isolators and circulators, fiber Bragg ratings, dielectric thin film filters, active optical components, tunable light sources. Wavelength division multiplexing scheme. What made WDM to originate? So when we see point-to-point communication link, it consists of optical sources and detectors. We even call it as an optoelectronic devices that are used on either side of the link. We found that these optoelectronic devices has some bandwidth limitations. It means that the sources cannot be modulated beyond certain frequency. In today's technology, it will be very difficult to modulate an optical sources beyond 10 gigabits per second, and same thing we can observe at the receiving end also. It is very difficult to detect the data rate which is higher than this range. This may be due to the limitations due to the electronic devices what we connect in the communication link, and people are experimenting on this up to 40 gigabits per second. However, it is still in experimental stages. If you have seen any deployments till now for the of these kind of systems, it is typically 10 gigabits per second systems only. This can also be due to the nonlinearity effects that are present in the optical fibers. Even though we have an optical nonlinearity effects, there are advantages of using these optical fibers because of its low loss, and it supports larger bandwidth and able to transmit huge amount of data. When we say optical fibers, it is having optical window ranges which are specified by ITU-T G.692 standards, and this optical transmission windows are also advantageous to use because it supports up to 30 terahertz. So in this figure you can see a plot which is showing attenuation versus wavelength. So basically you can see two types of windows. One is called a second window, that is ranging from 1270 to 1350 nanometer, and the third window we can see that is 1480 nanometer to 1600 nanometer. So the optical windows supports up to 30 terahertz approximately from these two windows, and this optical window range is reasonably having a less loss here, and these are specified by ITU-T G.692 standards, that is International Telecommunication Union standard. The thing is, we are not utilizing this 30 terahertz for the communication or transmission of data. So in case if you are using only one transmitter and one receiver, then it is said to be that the optical window is highly underutilized, and that is where essentially the origin of WDM exists. We are trying to exploit the maximum bandwidth which the optical fiber is offering us. So optical fiber has to make use of the bandwidth efficiently. That's the motto of the origin of the WDM. WDM systems. Some of the properties are listed here. An optical window ranging from 1.2 micrometer to 1.6 micrometer. So this range we call it as an optical window range because here the loss is reasonably small for the effective data transmission, and this supports up to 30 terahertz. In terms of communication channel, this bandwidth can support effectively 30,000 channels of 10 megabits per second. I mean, this is a kind of bandwidth typically needed to send a good quality video. Suppose if we are using entire bandwidth of optical window, we will be able to transmit 3 lakh video channels on a single optical fiber. So that is the one that is where we consider it as a huge capacity. So the limitation of the optical fiber is only lying in electrical devices which are used on either side of the link. So to exploit these 30 terahertz in the optical fiber, there are two possibilities. One possibility is by using time division multiplexing. However, if we are using time division multiplexing, it should effectively generate pulses of about a few tens of femtoseconds, which are highly impossible to generate such pulses. So hence we went for the second possibilities, and we can think of the second possibility, that is we should be able to use a bandwidth by dividing it into frequency bins, and these frequency bins should be transmitted independently. That means the information should be transmitted independently in each of these bins, and that is where we call it as an WDM. So in this case, we are accessing the bandwidth easily in case of WDM compared to TDM. What do we do in WDM systems? Basically, we divide the signal into multiple channels in optical domain. Each carrier is modulated by a maximum possible data rate, and all carriers simultaneously are transmitted in an optical fiber link. So initially when they designed this WDM systems, it was designed for two windows. One is for 1310 nanometer and another for 1550 nanometer, and they called the system as WDM system. So as the laser technology advanced, they started using multiple channels. So in this figure we can see a typical WDM network. So we have a transmitter, for example transmitter 1, which is operating at certain wavelength, that is lambda 1. Like that we can place n number of transmitters, and when I say transmitter here, there may be a whole network behind this. That means the data multiplexed from various locations are multiplexed and brought into this particular location called as transmitter 1, and the data which is present in the transmitter 1 is now riding towards the wavelength lambda 1. So similarly, we can have a time division multiplexed data which is coming here, and it is modulating for source from source lambda 2 and similar lambda 3 and so on. So then we have a device which is called as a wavelength multiplexer or a wavelength mux or a power combiner, where all these wavelengths are combined and you get one multiplexed output which is given to the optical fiber. So we can see that we have placed optical amplifiers. So these optical amplifiers are placed periodically depending upon the distance of optical fiber. So if this optical amplifiers has a bandwidth larger than the bandwidth of all together, then in one shot all wavelengths can be amplified in an amplifier, and that signal keeps on propagating with periodic amplification. So at the end, at the receiving end, we can see there is a wavelength demultiplexer. So the wavelengths are separated, that is lambda 1, lambda 2 and so on, and you get a signal back which is in time division multiplexed data, and each receiver will be receiving the original data which is sorted from here. Passive optical components used in WDM. These are called as passive components because these doesn't require external energy to perform their operations efficiently, and these are the components which operates completely in optical domain to split, combine the light streams, and they include following, that is N-cross N couplers, power splitters, power taps, star couplers and so on. 2x2 fiber coupler. So optical coupler are the one which is used to split the input signal and distributed power. So this device couples a part of transmitted power by specific factor through one port. And when we say optical fiber, the fabrication process is very simple, and this figure shows a 2x2 fiber coupler. So wherein it is constructed by twisting together, melting and pulling two single mode fibers so that they get fused together over uniform sections of length W. So W length is the one we call it as a coupling region, where energy is transferred from one port fiber to another fiber. And we also have a tapering region which is shown on either side of the coupling region. So it is represented by L. So initially input power is passed through port 0, and it will have two types of outputs. First one is throughput output, is also called as primary output, which is coming from port 1, and the energies are couples from port fiber 1 to fiber 2. It is obtained at port 2. We call it as a coupled power. And we also have port 3. Ideally the output at port 3 should be 0, but due to some reflections we get some form of crosstalk. We even call it as a reflected output. So the total draw length for the entire setup is given as LT is equal to 2L plus W. The typical values of this W and L are in a few millimeters. So also these 2x2 fiber couplers, since we are using tapers here, we call it as a fused biconical tapered couplers. Performance parameters of optical coupler. First one is splitting ratio. It is the percentage output power coupled in the coupler. We get two types of outputs in the fiber optic coupler, that is primary output and secondary output. When we say coupled output, it is P2. Total output power is given by P1 plus P2. Hence splitting ratio is given by P2 by P1 plus P2 into 100%. What do you mean by excess loss? Excess loss is the ratio of input power to total output power. Input power is P0 and our output power is P1 plus P2. Therefore 10 log of P0 by P1 plus P2. So loss is basically calculated in terms of decibels. So it is 10 log of P0 by P1 plus P2. Next we have to see what is insertion loss. So it is the loss for a particular port to port path, that is if input is given to ith port and output is to be given at jth port. So insertion loss is given by 10 log of Pi by Pj. I repeat, 10 log of Pi by Pj, where Pi is the input port and Pj is the output port. So here we have taken insertion loss of 10 log of P1 by P2, considering P1 is as input port and P2 as output port. Second we have if I'm considering P2 as input and P3 as output, so we can write insertion loss as 10 log of P2 by P3. So one more performance parameter we can see, that is return loss or crosstalk. So it is the ratio of reflected signal to the input signal. So we had taken a reflected output at port 3, hence we are considering 10 log of P3 by P0, where P3 gives the reflected output or the crosstalk and P0 is the input signal. So since these devices has some sort of reflections which are coming at port 3, these devices are also known as directional couplers. Let us consider the one problem on 2x2 fiber coupler. The given problem is for a 2x2 fiber coupler, input power is 200 microwatt, throughput is 90 microwatt, coupled power is 85 microwatt and crosstalk power is 6.3 microwatt. Compute the performance parameters of the fiber coupler. Write down the given parameters, that is P0 is 200 microwatt, P1 90 microwatt, P2 85 microwatt and P3 is 6.3 microwatt. So we know that the splitting ratio is given by P2 by P1 plus P2 into 100. So coupled output is 85, that is P2 by 90 plus 85 into 100 will give up to 48.57%, and excess loss is calculated as 10 log of P naught by P1 plus P2. Input power by total output power. So if you substitute the values, you will get around 0.58 dB. So if they ask insertion loss, it is 10 log of Pi by Pj. In general we know. Here we are considering 10 log of P naught by P1, where P naught is the input port and P1 is the output port. We are substituting the values accordingly and we get 3.46 dB. So if we consider path P0, that is port 0 to port 2, the insertion loss is given by 10 log of P0 by P2. So wherein we get 3.71 dB. The crosstalk is taken as 10 log of P3 by P0. So when we substitute the values, we get up to minus 45 decibels. We consider one more problem from the 2x2 tapers, where the problem is given as follows, where a 2x2 biconical tapered fiber coupler has an input optical power level of 250 microwatt. The output powers at other three ports are P1 is equal to 100 microwatt, P2 90 microwatt and P3 6 nanowatt. Calculate insertion loss between 0 and 1 port, insertion loss between port 0 and port 2, coupling ratio and return loss. Write down the given data. So at a power level of 250 microwatt, input power level they mentioned in the question. So we can take P naught as 250 microwatt, P1, P2, P3 they have given. They told to find out the insertion loss between port 0 and port 1. Therefore it becomes 10 log of P naught by P1. So if we substitute the values, given values, you will get 3.9 dB. Similarly, in the second they had given a path between 0 and 2. It means that port 0 by port 2. Port 0 is considered as input port and port 2 as output port. So 10 log of P naught by P2. If we substitute the given values, we get 4.42 dB. Coupling ratio is given by P2 by P1 plus P2. So getting up to 47.37%. So coupling ratio is nothing but the splitting ratio. So return loss is nothing but the crosstalk. So 10 log of P3 by P0. So it is 6 nano. So 6 into 10 raised to minus 9 by P0 is input power. 10 log of that ratio we get minus 46.1 dB.